we have a lot of electricity needs in our modern society. If you look around the room that you're in right now, probably you see a multitude of plugs, and maybe there are some things plugged into those plugs. So we rely on electricity for our everyday lives. We produce that electricity not anywhere nearby where we live, but in our case, in Manitoba, we produce it up north. And that electricity that's produced up north has to somehow make it south to where we live. And we do that using something called transformers. Okay, but that's really just a middle step along the way. So I've drawn you some pictures over here in the top left corner of your page. We've got a hydroelectric dam over here. Okay, the hydroelectric dam has a bunch of coils of wire in it, inside magnetic fields, and the coils of wire spin as the water rushes past them. And then it's a little bit more complicated than that, but we can get into that in the AC generation station next, the AC generation section next. But you get, because of that change in flux that's happening, you get a voltage that's produced. Okay, but the voltage that's produced is not the right voltage for what we use at our houses. Okay, in our houses we use 120 volts in our part of the world. In Europe you'd find 220, and then there are various other small differences elsewhere. But in order for our electronics in our houses to work, we have to have voltage delivered to us at 120 volts or 110. There's some wiggle room in there. So the voltage that's produced at the generating station is not the same as what's at our houses, but it's also not the same as what's used to transmit that electricity all the way to where we live. Okay, so here's what happens. We produce the electricity at the generating station. It goes through a transformer. So that's just a little mock-up of a transformer. Google it. It goes through a transformer which steps up the voltage really, really high. And then the high voltage is transmitted over transmission lines to where we are, and then probably near where you live there is another distribution station of some kind. At that distribution station, you have another transformer, and that transformer is going to step down the voltage to something that's closer to what's usable for your house, and then probably somewhere around where you live, very nearby, there's another transformer. Some of those transformers are pole-mounted transformers. You'll see this kind of gray cylinder on a hydro pole. And some of you, especially in town, are going to have this green box on the ground somewhere near where you live. Maybe in your front yard, maybe in your neighbor's yard. But a transformer of that variety only serves a few houses at once. So most people need to be really near one. And that last transformer, it steps down the voltage one more time to 110 or 120, whatever is being used in your house. So transformers are a way of changing voltage. Now we need to amp up the voltage really high in order to transmit the electricity down the wires because of this relationship. P equals IV. This is power equals current times voltage. So here's what that means. Power is how much electricity there is, or how much energy is being transmitted per second. Okay, so the amount of energy that's being transmitted per second, or generated per second in this case, it has to be the same as what is being delivered per second. That's a conservation of energy thing. Okay, so the power at the beginning, at the generating station, has to be the same as the power where it's delivered. So if we bring the voltage really high at the generating station, what can happen then is we can transmit that power at very low current. Now that's important because if you would transmit very high current through our power lines, through hydro lines, they end up producing a lot of heat. Okay, they heat up the lines really hot, which means that some energy is just going to be lost, which means that that transmission becomes less efficient than it could be. Okay, it also isn't good for the for the wires to heat up really hot either, right? So if you heat up metal wires, they're going to expand. And if you set it in your mind to take notice, you'll notice that in the wintertime, there's less line sag than in summertime, because in summertime the lines are warmer than in wintertime. Okay, and so there's also an aspect of caring for our electricity distribution equipment that needs to come into play as well. So the goal here is to jack up the voltage really high so that you only need a small amount of current in the wires to get the same amount of power out the other side. Okay, and so that's important. We need to increase the voltage so we can have low current and low energy loss. So that stepping up of voltage happens at the AC generating station. Then that voltage is transmitted across the lines all the way to where we are. And then you get over here. This is a distribution station. You have another transformer there that's going to take that really, really high voltage, possibly 100,000 volts, possibly 30,000 volts. It depends on the system, really. And it's going to step it down again to a lower voltage. Then that lower voltage gets passed on to yet another transformer. This is a residential transformer right over here. And that residential transformer will step it down one last time to what your house actually uses. Okay, so we need transformers in order to get electricity most efficiently from the generating station to where we use it. So that's what transformers are for. Now, again, I would suggest that you Google transformer. You might have to do more than that because you just might get some robots then. But electricity transformer, residential transformer, pole-mounted transformer, pad-mounted transformer, those types of things, you'll get the right thing. Okay, now here's how a transformer actually works. This is a very simple transformer right over here. It consists of an iron core, which is the purple part. It's just a rectangular ring or square ring, whatever. It doesn't really matter. On one side, you have a coil of wire that's been wrapped around the transformer core, and that would be called the primary coil. So this side over here, this is the primary side. The primary side of the transformer. Okay, that's electricity is incoming. Incoming from the generating station, incoming from the distribution station, whatever you have. So you've got incoming electricity. That electricity goes around the coil and then exits the coil again. Okay, now it's going to be alternating current. Has to be alternating current. Okay, and so the direction that I've drawn here, it doesn't really matter because it's going to flip back and forth anyway. But here's what happens. Whenever you run electricity through a set of coils, like the one on that transformer, like this one, when you run electricity through it, we know that that produces a magnetic field, right? And that magnetic field is going to point in whatever direction based on the right-hand rule. And because it's wrapped around an iron core, that magnetic field passes through the entire iron core. So let's say that our magnetic field then, well, let me do the right-hand rule correctly here. Here we go. So our magnetic field then passes through the coils this direction, like that. Okay, and then it's going to pass through these coils as well. Okay, so there's our magnetic field. Now again, this is alternating current, and so the direction of the current is going to flip back and forth 60 times a second, and that means that you're going to get a changing magnetic field through those loops over and over again. So the incoming electricity is producing a magnetic field through the coils, through the primary coil, and that magnetic field is being shared with the secondary side. Okay, so the other side is going to be called the secondary side or the outgoing side. Okay, so the primary side is the incoming electricity. The secondary side is delivering that electricity to the next stage of the electricity transportation system. We can call it that for now. That field is being transmitted to the secondary coil, and then we know from induction that when you have a changing magnetic field inside a set of coils, inside a coil of wire, it's going to produce a current, right? A current depending on what direction the change is happening in. And so on the secondary side here, we are also going to get current passing through that wire. Now, maybe it's this direction and this direction. Again, since it's AC, since it's alternating current, it's going to flip back and forth all the time. It has to be AC. If it was not AC, the moment you turned on the direct current, which only flows one direction, you would get a magnetic field just for the duration of turning it on, and then that magnetic field would disappear, right? And then you wouldn't get any induced current in the secondary coil. You would only get it for that moment when you're turning it on or turning it off. But AC, because it's constantly changing, makes sure that you get induced current in the secondary coil all the time. Okay, so that's how we change voltage from one side to another, by taking voltage, or by taking a changing magnetic field from one side of a transformer and sharing it with the other side. The change happens because the number of coils on the primary side versus the secondary side differs. So check this out. The primary side here, I've got 4 coils. On the secondary side, I only have 2 coils. And we know from our Faraday's law formula, N change in flux over T, the number of coils is directly related to how much voltage you get. And so in this case, the first transformer I've drawn here is called a step-down transformer. Step down. Okay, it's a step-down transformer because it takes high voltage on the primary side and makes it smaller on the secondary side by reducing the number of coils. And in fact, you're going to get half the amount of voltage on the secondary side because we've reduced the number of coils by half. Okay, so that's called a step-down transformer. That would be a residential transformer that takes current, or that takes voltage from the distribution center near your town, in your town, and steps it down so that your house can use it. Okay, there's another type of transformer. I mean, all you need really is some sort of ferromagnetic core that has 2 different coils of wire wrapped around it that are not attached to each other. And so the second one here we have is another type. We have our primary side there and our secondary side there, and the same thing will happen. So you'll get incoming current over here that's flipping back and forth, and so you get a field that is produced within that set of coils, which then also magnetizes the second set of coils, which through electromagnetic induction will induce a current in the secondary side. Okay, and so in this case, this one would be called a step-up transformer. This one is a step-up transformer because it has more coils on the secondary side, right? The primary side has 2 coils. The secondary side has 1, 2, 3, 4, 5, 6 coils. And so the amount of voltage you get on the secondary side will be 3 times the amount of voltage you got on the primary side. Okay, and so this would be a step-up transformer. This is what you would want at the generating station to amp up the voltage really high so that you can transmit it efficiently. So like we said, changing the number of coils on the secondary side versus the primary side, that's how you change the voltage from one side to the other. And we just said that it's a direct relationship. So if you double the number of coils, you're going to double the voltage. If you cut the number of coils in half, you're going to cut the voltage in half. And so the relationship looks like this. The voltage on the primary side, Vp, over the voltage on the secondary side, Vs. So the relationship, or the ratio of the voltages, is equal to the ratio of the number of loops, or the number of coils. Vp over Vs equals Np over Ns. Okay, so this up here is the primary voltage. And the bottom is the secondary. And we have the number of loops on the other side. Number of primary loops. Loops, coils. I think there's a different word that is sometimes used. I don't even remember. But whenever you see that, you'll know what it's talking about. Number of secondary. Okay. So those two ratios are going to be the same. If you want to double the voltage, you need to double the number of coils, etc. You get the idea. So step-up transformers take a small primary voltage and make it a larger secondary voltage, which means that you have to have a small number of coils on the primary side and a larger number of coils on the secondary side. That would be a step-up transformer. And a step-down transformer is exactly the opposite. Okay, so two types of transformers. They're just used in different spots in electricity transmission. Okay, so power, though, we said that the power at the generating station has to be the same as the power that is provided to our households. Okay, that's a conservation of energy thing. So more voltage does not mean that the power has changed. The power has stayed the same. But that does mean that the current has to change. So we know that the primary power has to equal the secondary power. Okay, conservation of energy. And our formula for power is IV, current times voltage. So this is primary current times primary voltage. Let's fix that. Primary current times primary voltage equals secondary current times secondary voltage. Okay, so you can use that relationship just like it is, or we can change it to a ratios thing as well, which is not as nice for algebra purposes when you're actually solving problems with this thing, but it is good for understanding this relationship. Okay, so we're going to rearrange this just a little bit to have the voltages on one side and the currents on the other side. So I'm going to move the voltages to the left side and the currents to the right side. And that means we have primary voltage over secondary voltage equals secondary current over primary current. The relationship is reversed. So if you look back at the relationship between voltages and number of coils, you get a direct relationship. Okay? If you double the voltage, you have to double the number of coils. It's the opposite with voltage and current. If you want to double the voltage, you're going to cut the current in half. Okay, and that's exactly what we wanted, right? When we step up the voltage really high at the generating station, the point of that is lowering the current as much as possible so that the lines don't heat up and so you don't lose heat energy that way. Okay, and so you get an inverse relationship with the voltage and current compared to the voltage and number of loops. And you could say the same thing for the number of loops, right? So because we know that Vp over Vs is the same thing as Np over Ns, we can also see that the relationship between the current and the number of loops is also an inverse one. Let's try a couple examples. What is the ratio of turns for a transformer that requires a 4-volt output from a 120-volt input source? Okay, so 120 volts, that's the primary, and the 4-volt output, that would be the secondary. Okay, what is an example of a number of turns of such a transformer? So first of all, we're trying to figure out what's the ratio here. It doesn't tell us how many turns. Oh, that's the other word, turns. So coils, loops, turns, those are all the same thing. It doesn't tell us how many turns there are on the primary side or the secondary side, so we can't actually solve for either of those numbers, but it's asking us just for what the relationship is between them. Are we doubling the number of coils? Are we tripling the number of coils? That's the idea. So let's take Vp over Vs equals Np over Ns. It gives us Vp and Vs, and really what it's asking us for is this whole thing. What's this whole ratio, the whole fraction? So Vp is 120 volts. Vs is 4 volts. And all it's asking us to do here is make it a reduced fraction. So if we divide both of these, both of the top and bottom by 4, then you get 30 over 1. Okay, so the ratio of turns will be 30 to 1, primary to secondary. So this is a step down transformer, right? So 30 to 1, this is our ratio of turns. So what's an example of a number of turns? I mean, you could have 30 turns on the primary side and 1 turn on the secondary side. Or you could have 60 turns on the primary side and 2 on the secondary side, etc. 90 to 3, whatever 30 to 1 you can come up with, it's going to work. Let's try the second one. A step-up transformer has a primary coil with 200 turns and a secondary coil consisting of 3,000 turns. Okay, so I can see already that that is indeed a step-up transformer because it has much more turns on the secondary side than on the primary side. The primary coil is supplied with an AC voltage of 90 volts. So that's the primary voltage. What is the output voltage? So what's the secondary voltage? So we've got Vp over Vs equals Np over Ns. And so we have Np here, and we have Ns over there, and we have our Vp. We have our primary voltage there, and we're trying to solve for our secondary voltage. So you are more than welcome to flip the entire relationship upside down if you like, if that makes the algebra easier for you. But what we end up with, either way, is Vs is equal to Vp times Ns over Np. Okay, check that algebra for yourself. Vp is 90 volts times the secondary number of turns, which is 3,000, divided by the primary number of turns, which was 200. And so you should get a secondary voltage of 1,350 volts. Okay, now just to check, we knew that this was a step-up transformer, and so the secondary voltage should be higher than the primary voltage. Right? And it is. Our primary voltage was 90 volts and our secondary is 1,350. So at least logically that makes sense. In the second part, if the current in the secondary circuit is 2 amps, what is the current in the primary circuit? Okay, so for this I want to use IP Vp is equal to Is Vs, right? So I'm using that version just because the algebra is easier with it. You are more than welcome to use IP over Is is equal to Vs over Vp. Just that inverse relationship. You're more than welcome to use that thing if you want, but this version is going to be a little bit simpler. So we're looking for the current in the primary circuit. So that's IP. That's going to equal ISVS over VP. Okay, and we have all three of those things. The current in the secondary circuit is 2 amps. The voltage in the secondary circuit is 1,350 volts. And the voltage in the primary circuit was 90 volts. And so our primary current is going to be 30 amps.